about using the definition of the derivative to find the derivative functions of the form x raised to 1 over a power, for example, x to the 1/2, x to the 1/3, x to the 1/4. Now, there's a handy little rule to do that, very, very quick shortcut, but a lot of calculus teachers would prefer you know the algebra behind the limit definition of the derivative. Now, the most common one I've seen is find the derivative of x to the 1/3 power using the limit definition of the derivative. Now, before we get into this, I want to tie that back to the more common case, x to the 1/2 or the square root of x. Now, you may not have seen it done exactly like this, but it turns out this difference of two squares formula comes into play quite a bit for this type of problem. So we're trying to find the derivative of x to the 1/2 using the limit definition. And I've already got written down the majority of the steps here. The limit definition is basically just a limit statement married to a slope formula. Really, this is like y2 minus y1 over x2 minus x1. We're just using functional notation. When you marry that to a limit, you get a tangent line as the function approaches the value a. Now, so let's understand how this identity comes into play. Like, okay, now if you take a look right here at this part that I have highlighted, folks, the key to when you write down the limit definition, and a lot of people just get stuck right here. I know I did. Like, okay, what do you do now? But what makes this thing fly is that if you recognize this highlighted piece as the difference of two squares. That's kind of a crazy thing to observe, but once you see why it works, you won't forget it. It works exactly because of this truth right here. A squared minus b squared is equal to a minus b times a plus b. That's what they call an algebraic identity. And so if we write this highlighted piece as the square root of x squared minus the square root of a squared, we have it written in the difference of two squares. Remember that this piece right here is literally equal by definition of exponents, right? This piece right here is literally equal to this piece right here. Now, the reason why it's useful to write it that way is now it admits to this form a minus b, a plus b. You see, we're just literally using this. A squared minus b squared is equal to a minus b times a plus b. And so we've gone from here to here to here. But why is this advantageous? Well, notice now we have common factors. This piece isn't in parentheses, but this would be a factor that would cancel with this factor in the limit. See? As long as x is not equal to a, you're not doing anything crazy like dividing by 0. You're just approaching a. This says as x approaches a. So you can actually cancel this factor with this factor, leading to this. All right, and now if you've done your algebra right, the limit is usually very easy to take. Notice that this says as x approaches a. Well, a is a dead constant, so you can't substitute in there. It's already there. But you can replace this x with a. That's one of the properties of limits. It's called the substitution property of limits. It says you can make a substitution as long as you're not inducing a division by 0. So if you put a in right here, you get 1 over a. You get a to the 1/2 plus a to the 1/2. But that's 2 of them, right? That's 2 of them, and you get this result right here, a well-known result. Sometimes you would write this as 1 over 2 times the square root of x by properties of rational notation, or properties of negative exponents. But y'all, I hope that's kind of a quick one to see what it'll be like to handle the case x to the 1/3. Again, we depended on an algebraic identity to do this case, and we got the correct answer. Now, this is kind of tedious. I like writing the limit statements, and a lot of people will say, well, just do the algebra and then put the limit back in there. I don't like doing that. Notice that the limit did disappear on this step. You see, this still is a limit statement. But once we took the limit, that is, replaced x with a, this is what we got. All right, so again, this is here for you to look at again on the video. But now let's go back to the original problem. All right, now, so here, the only difference between this problem and the last problem is this is x to the 1/3, right? X to the 1/3. Now let's bring up the stuff here and see how it compares to the last thing we did. All right, now the key, and this I agree, this isn't the easiest thing in the world to see, is to realize that this identity, is useful. All right, now it's a very similar sort of process. All right, now this is the difference of two cubes formula, and it's going to bail us out very much like the difference of two squares formula did. And again, I can talk and talk and talk. You guys can just look. The key is to rewrite this piece right here as the difference of two cubes. That's the key. This highlighted piece here, this highlighted piece, and it looks kind of contrived, but once you see why you're doing it, like I said earlier, it's kind of easy to recall. This highlighted piece here equals to this entire denominator right here. Just this, I can't make them both highlighted, folks. I don't know how to do that. But anyway, this is the highlighted piece. We used this identity to replace this highlighted piece right here with this part where my cursor is waving. Okay. We have it written as the difference of two cubes. And now the sound and the fury of this identity is unleashed. We can re-express this piece right here as this entire piece right here. This says a cubed minus b cubed, right, folks? Right here, a cubed minus b cubed. Now this is a minus b, and then the rest of this identity. See, this is your a minus b piece right here. This would be your a squared piece, your ab piece, and your b squared piece. And again, once you substitute a in everywhere there's an x, you get 3 copies of a to the 2/3 power. Notice that a to the 1/3, a to the 1/3 is a to the 2/3. And there's 3 of them, and they're in the denominator. So this answer right here would be acceptable. Some people want you to write your answer with negative exponents. That's really not that big a deal. Nobody should make a big deal about that. All right, now, so I hope you like that, folks. The key is to use these identities, and that's the obscure part that's kind of hard. You know, you go, what? You know, how do you know to use that? But it turns out there's an identity like that for each one of these type of problems. Now, let's come down, and here's a practice problem for you. All right, as you may have anticipated, for x to the 1/4, you have this identity comes to bat for you, and it rescues you. It's really kind of neat how it all works out. There's for every case, you know, 4, 5, 6, 7, 8, there's an identity like this. All right, and so notice there's 4 terms in this right here, and that'll come into play if you actually want to take the time to practice this and solve this. But I'm confident if you understood what I went over that you can do this fairly easily. It's tedious but not difficult. Okay, I hope that helped.